7 elements that always exist as a dimer, meaning there's 2 of them together, a molecule of 2 parts, like oxygen is O2. The reasons for that are because of their valence electrons, how they join up, the way we've talked about that before. But it's probably useful for these type of problems if you just remember them, that they are H2, N2, O2, and then this column 7, group 7. So those 7 always exist as 2. So when you see something say oxygen or oxygen gas, you know it's O2. If it says hydrogen or hydrogen gas, it's not just H, it's H2. If it says bromine, which is a liquid, it's Br2. So those 7 always exist. If you really just remember 4 things, H, N, O, and then the last group 7 there, that whole line. So then looked like a lot of you got that the equation would look something like this. Dihydrogen sulfide and oxygen react to form sulfur dioxide, SO2, and water vapor. And I didn't put the phases in here, but they would all be G for gas. So this is the equation. Is it balanced? It's not. It's not. So we need to do that. The hydrogens are balanced, the sulfurs are balanced. This actually is a very similar equation to the last one we just did, in that you can't balance the oxygens properly because you can only go in 2s on the left, but yet there's 3 on the right. So what are you going to do about that? Well, you need to double everything. So we'll go 2, 2, and 2. Now we recount, and we find that there are 6 oxygens on the right, and so then we can put a 3 here to balance that. All right, so if you didn't get that, take a couple more minutes now to work on the calculation part, see if you can get part B now that we have the correct equation. And then if you've done that, the question is asking for, if you have 2.5 grams of this, how much of this do you need? If you've done that, see if you can also find this and this. For what number? Well, you have to set up this kind of a plan. Yeah. So you start with 2.5 grams of H2S. You use the molar mass here, so H2S, moles of H2S, and moles of H2S to moles of O2, and moles of O2 grams of O2.
So first H2S, then O2, then O2.
Well, first you have to go to moles, grams to moles, and then moles of H2S to moles of O2, then moles of O2, grams of O2. let's take a look at this one together. So once again, we're going to go with the same plan. We start with grams of H2S, then to moles of H2S, moles of O2, grams of O2. Right? Same plan. All right, let's set that up. So grams to moles, H2S, moles H2S to moles of whatever else we're looking for, in this case O2, and then mole O2 to grams of O2. All right, now we just need to fill in the numbers. So that's about 34 for H2S, 34.02 if you want to be more specific, but that's fine. Then for the next numbers, we use the equation. So that's 3O2 to 2H2S. And then finally, we find the molar mass of oxygen, which is 32. That's 2.5 divided by 34 times 3 divided by 2 times 32. 3.53. Did you get something like that? Close? All right. Let's look at the other two, because that gives us one more important thing, especially for lab next week. So we can just take this exact same equation, change the numbers that we need for each of the other ones. So I'm going to take this whole thing, just copy it, paste it, and let's say I want SO2 instead. Beginning part's all the same. The last part is what changes. So let's set up our new thing here. But now instead of O2, we're going to go from H2S to SO2, and then SO2 over here. So the new numbers are, again, from the equation 2 to 2. And SO2, that's going to be 32 plus 16 plus 16 is 64. That's 4.71. All right, so exact same technique, just with a different product. And we could do the same thing with H2O, or we could just add the reactants, 2.5 and 3.53, subtract 4.71, and that's how much oxygen there should be left, because the masses have to equal on both sides. One more term that we should know is here. This is called theoretical yield. So when you do a reaction, one thing you often want to know is how much of this product am I going to make? Often it's the opposite. You say, I want 5 grams of product. How much of stuff do I need to start with? But you also want to know how much of this stuff do I expect to make? So 4.71 grams of SO2 is how much you would make if you reacted 2.50 grams of H2S and 3.53 grams of O2, and every molecule exactly worked and went to the product. Now, in real life, that's not going to happen. Every reaction is going to have some amount of loss, whether it's just stuff doesn't work properly or just the energetics of things going back and forth. There's no perfect reaction for the most part. So that's called the theoretical yield. How much could we possibly make at the very most? And then often what we do in lab, and what we will do on Wednesday, is we'll measure how much we actually get against the theoretical yield and get something called the percent yield, which is what percent of the theoretical yield did we actually make. If it's, and different reactions will have different values for that. So maybe one reaction you want to get 90% yield, which means 90% of what you could have made. Some reactions maybe don't work that well. Maybe you only get 50% yield, something like that. So when you see chemical reactions published in papers or in drug synthesis, that kind of stuff, they'll often report percent yields based on a theoretical yield like this. And a big part of drug development is trying to increase those percent yields, trying to make it more efficient. Okay. So what part of this process would you say you're having the most trouble with? What part isn't working so well?
I'm still stuck on the very beginning.
Just writing the compounds
down?
down?
Once I get past the beginning, and it's a little more clear.
Okay.
I'm still struggling with making the equation and stuff.
All right, so let's work on that for a little bit here. Let's pull up some more examples from the book and make sure. And that's a common issue and something that you really need, it's tough to get right, and then you can't go on until you get that part right? So let's take a look at some of the examples from here. Zoom out here so I can see. So I want to pick out a couple of these because it will also help us to try to look at a couple other things too. Take a look at these equations. And then we'll get back to the math part if we need to. So the question in the book here is just what category do these equations fit into? But I think it's worth being able to write these down as actual equations too. Now the first one doesn't quite work that way because we're not given any specifics. But what kind of a reaction is that? That first one, a compound of hydrogen and carbon reacts with oxygen to produce carbon dioxide and water. What category of reaction does that fall into? Not quite. Not quite. Nope. Combustion, yeah, this is combustion. Reacting a hydrocarbon with water to produce, or with oxygen to produce carbon dioxide and water. That's a very specific one. That's pretty much only what we call combustion in this case. So yeah, let's write that down. This is combustion. And there was another one.
So it always form carbon dioxide and
Right.
water. This is combustion.
Yes, that's really what you're looking for here. And there's one more I was going to grab here too. Oh yeah, these. All right, so these other 5 here, we should be able to write down a chemical equation for these. But it's going to take a little bit of thinking about what category the reaction is in and how we're going to write those compounds. So let me show you an example. C is pretty straightforward. You write the stuff down just as it says. But let's look at D, because D doesn't give you quite as much information. Zinc replaces copper in copper 2 nitrate. How would we write an equation for something like that? What is that saying? Well, what category of reaction would it be in? Single replacement. So we think about what that means. That means you have one thing by itself and then a compound, and then the thing by itself switches with the thing in the compound. So how would that work here? Yeah. So we'd say zinc, which we know is a solid metal, plus copper nitrate, which is a solution, although it's not said here. And then what would the products be? Zinc and nitrate. So we have to figure out how to make a compound from zinc and nitrate. And then what would another product be? Copper, right, copper metal. So that would be by itself. And then we have to figure out how to make a compound of zinc and nitrate. Anybody know, this is a tricky one, but what's the charge on zinc? It's 2, yeah, even though it's in a weird place, it's always +2. So that means that it's going to have the same type of a compound as copper 2. And this is a reaction that we did, maybe not this exact, did we do this exact reaction yesterday? Something very similar to it. All right. See if you can write equations for each of the rest of these. That is this one, this one, this one, and this one. I have to tell you one thing, because there's one ion that's not on the list here, and that is sulfite, which is SO3 2-. I would not expect you to do that one, to know that one. See if you can come up with equations for each of these. Now you're going to have to categorize them, I think, to be able to write the equation. Once you've got it in the category, see if you can write down the equation. And then ask around and see how other people's equations looked. All right, so let's take a look at some of these. Hopefully you got C because that was what we did in lab yesterday. Calcium carbonate is CaCO3. And heating it produces calcium oxide and carbon dioxide. Again, carbonate, CO3 2 minus, that's one from the list. You should know that one. Calcium 2 plus from the second column. And then copper and bromine form copper 2 bromide. So let's take a look at that one. Copper is just Cu. Oh no, we're doing this again? Okay, there. Copper is Cu. Bromine, remember, that's one of those ones that we just talked about that needs a double. So that's going to be Br2. And it doesn't tell you this, that's actually a liquid. You wouldn't know that but necessarily, but it's a liquid. Again, I won't ever mark you down for having the states wrong on these things, the S, L, G, A, Q. That doesn't matter quite as much. Copper 2 bromide. Copper 2 is copper 2 plus, and bromide is Br minus. So that means we're going to need 2 of those to go with the 2 plus. So that's CuBr2. And that's balanced just as is. I think all these are pretty well balanced just as they are. Then iron 2 sulfite breaks down. So sulfite I gave you, SO3 2 minus. Iron 2 is Fe2 plus. So that means that there's going to be a 1-to-1 type relationship. And that breaks down to iron 2 oxide. Again, oxide is 2 minus. So 2 plus 2 minus should be just FeO. And sulfur dioxide, SO2. And those are balanced as well. And then finally, this one doesn't really tell you the products, but it says silver ion from silver nitrate, AgNO3, forms a solid with bromide ion from KBr. So what do you think that means? What is that telling you? That it's going to be probably a double replacement. So we can first just write down exactly what they say. So we've got AgNO3 and KBr, and it says the silver forms a solid with the bromide ion. So that means the silver is going with the bromide ion to form a solid precipitate. Now we didn't know that it's necessarily that it's 1-to-1, except that from the first compound there we can see that silver must be +1 because nitrate is -1. But we sometimes have to adjust ratios in there. And then AgBr, So then what must be left, since we can't lose anything, are the other two pieces, the K and the NO3. Something like that. All right. So try to figure out where you're struggling with this, if you still are. Probably, I would guess it's writing down the compounds and getting the compounds correct. So that's actually go back to the previous chapter, chapter 5, I think that is, and we're 6. Shoot, back here. Let's take a look at that. I don't want to tell you the wrong thing here. 6, chapter 6. So make sure you go back there and practice a little more. I've also posted extra stuff in the notes folder, extra practice on the naming and writing compounds, because that's, again, important in this chapter as well. So just to make sure that we're good, since we've worked on that part a little bit, let's go and just work on the molar calculations, second part of that, before putting it all together again. So here's an example where you're given the equation. Oops, not that one. We'll do a couple of these for homework. You're given the equation, and then you're asked to do some calculations. So let's take a look at this first. All right, so there's 3 parts. The equation is given, 4Na plus O2 is 2Na2O. The equation is given, and you've got 4 mass calculations, which are all basically the same problem, just with different numbers. First, you're given Na grams, and you have to calculate Na2O. Then you're given Na grams, you have to calculate O2, and then you're given Na2O grams, and you have to calculate O2. Your technique should not change for each of these. You should be able to essentially copy and paste what you do, the expression that you write down for each of these. So give these a try, and we'll see how they go. Let me know if you're stuck.
We have to do all three.
Give them a try if you've got time. We'll stop in a couple minutes and look at them. All right, so let's take a look at the basic technique here. We're gonna set it up just like before. $57.5 grams of Na. And we're gonna convert grams of Na to moles of Na using the molar mass, and then moles of Na to moles of Na2O. And then finally, converting those moles of Na2O to grams of Na2O. All right. Grams to moles, moles to moles, moles to grams. Same as everything else. So in there we put 23 grams per mole from the periodic table. The equation tells us 4 to 2 here. And then finally, sodium oxide, that's going to be 46 and 16, which is 62. So that tells us that with 57.5 grams of sodium, we would make 77.5 grams of sodium oxide. Is that what you got? No? Some? Yes? What'd you get? How'd you do it differently?
Well, I came up with 38 instead of 23.
Oh, okay.
That's why I'm wrong.
Okay, so if you used the 23, it would have worked out okay? Okay. All right. That's fine. Yeah, which is a good point, actually, when you're doing problems like this on the exam, even if you're really good at them, or on a quiz, if you're really good at them, write them out like this. Because if there is a mistake, like you used 38 instead of 23 or something, I'll see that, and I'll say, oh, well, it's all set up right. You just wrote the wrong number here. That's still worth most of the points. When I would do a calculation like this in a notebook, like doing research, I would write it out also, because then if something goes wrong or if it doesn't seem to work, you can go back and check your calculations. If there's just a number written there, you don't know how you came up with that number. You don't know where the mistake might be. So it's always useful to write out the stuff in lab or in on exams, so you can find where the mistakes are. The only exception to that, I guess, is multiple choice exams, because it is what it is. All right, do you want to see these other ones, or go on and do something else for the last 10 minutes or so? Any preference? Everybody's good? What? Do the rest of them? Okay. All right, 18.0 grams of Na. And this time we're going from Na to O2. So it all looks the same, except we start with Na and we end up with O2. What? Isn't that right?
No, you're right.
Yeah, okay. All right, so I call this O2. And then the last one, we start with 75 grams of Na2O. Now we're going to go to O2. Okay, set up in the same way. So Na2O is 62. The equation tells us it is, I think, 2 to 1 or 1 to 2. Okay. This is a little more commonly how we would do this in a research setting. We want to make a certain amount of the product, and so we want to know how much of the reactant we need to then actually do that. And so we'll do a quiz on this on Tuesday. Lab on Wednesday will be this. We'll be actually doing the reactions and then calculating how the moles worked out. And a couple of the reactions are ones you've already done this week, so you kind of have a sense of how they work. You can do them a little bit more carefully and make sure that you get the correct number of all the stuff. All right, so we got about 10 more minutes. What do you want to do? Practice? All right. All right, let's practice writing one of the equations from lab yesterday. Trying to remember what it was. It was cobalt nitrate in lab yesterday? Yeah, okay. All right, so don't pull that stuff out because I don't want you to look at the equations, but let's look at cobalt nitrate. And we're going to add sodium hydroxide. And I want you to write a balanced equation for this reaction. Cobalt 2 nitrate, sodium hydroxide. So you have to put these together, and don't look it up and don't look at your notes and don't remember what you did yesterday, but just kind of try to put these together because this will illustrate one other thing that sometimes comes up. Remember that this was a double replacement reaction, so you've got two ionic compounds. That means the ions are going to switch. right, let's look at the compounds first. Cobalt 2 nitrate is going to be CONO3 2. And then sodium hydroxide, NaOH. A part of the reason I wrote them in words is because double replacement reactions actually work better if you look at the words before you look at the formulas. Because one problem that people run into is switching everything and not redoing the ratios. So in other words, it's easy to say, oh, cobalt hydroxide. So I go COOH and NaNO3 2. But it doesn't work that way because they have different charges. Cobalt 2 is +2 and sodium is +1. So what really happens in the double replacement reaction is that cobalt 2 goes with the hydroxide. So we end up with cobalt 2 hydroxide, and the sodium goes with the nitrate. So when you do it in words, you can just switch them. Exactly. You can like just take the words and switch them and put them together. But the compounds are going to be a little bit different. Cobalt 2 is +2, hydroxide is -1. So you need 2 hydroxides for each cobalt 2. So that means cobalt 2 hydroxide looks like this. Sodium is +1, nitrate is -1. So sodium nitrate looks like NaNO3. And then is that balanced? It's not, no. So we need 2 of these, 2 of these. That should be the balanced equation. So if you're having trouble, or if you notice when you're practicing this, that when you write down double replacement reactions, you forget to redo the ratios, you can try doing them in words first and switch the words and then write the new compounds. Sometimes that's helpful, sometimes it's not, but whatever works for you is good. Okay, so keep practicing this. We'll do a quiz on Tuesday. I think everyone here should know exactly what's going to be on the quiz on Tuesday. Shouldn't be any surprise. So keep working on writing down the compounds from names, writing chemical equations and balancing them, and doing the math of calculating one when you're given the other one. That's what will be on the quiz on Tuesday. All right, and have a good weekend.